Hello, today we present our project of mechanics of machine, and the subject is the Singer sewing machine. So this is the table of contents. In our mechanics of machine course project, we focus on the needle mechanisms of a sewing machine, which converts motor rotary motion into precise linear and oscillatory movements for stitching. Our objectives were to design a CAD model, perform kinematic and dynamic analysis, and validate performance using Excel and ANSYS machines. The report includes the mechanisms operations, market designs, and design rotational, while the project highlights the application of theoretical concepts to a real-world system. This work enhances our understanding of motion conversion, mechanical designs, and system efficiency, combining hands-on and analytical skills.
So, for the description of the sewing machine, the basic functioning of a sewing machine relies on several key mechanisms. The vertical movement of the needle is controlled by a slider crank system, converting the motor's rotary motion into reciprocating motion. This motion allows the needle to pierce the fabric and form a stitch by looping the upper thread around the lower thread. And the feed dogs, small metal teeth, move the fabric beneath the needle in sync using a cam mechanism. This ensures smooth fabric advancement and consistent stitch length. Key mechanisms include the crankshaft for needle motions, the bobbin and shuttle system for stitch formation, and the fabric feed mechanisms and the tension regulator to adjust thread tension. These components work together to ensure precise and efficient stitching. And in our study, we focused specifically on the motion of the needle driven by the motor. This is a critical aspect, as the conversion of the motor's rotary motion into the precise vertical motion of the needle directly affects the machine's stitching performance and quality.
So, our study focuses on the upper part of the sewing machine, namely the control movement of the needle. The lower part, which includes the movement of the fabric, will therefore not be taken into account here. The mechanism is based on a belt pulley system. The motor drives the belt, which stands the upper pulley, and drives the key mechanism. As shown on the slide, speed and rotational speed relationships are used to configure the size of the pulleys. On the same system as a piston, the drive wheel allows the needle to be moved up and down using a slide. By modeling the mechanism in ANSYS, we can add initial values in order to numerically simulate and make a speed acceleration or positional study.
So now I'm going to calculate the velocity at point C. So here is a simple representation of the principle of the sewing machine with the needle at the point C. So we start by calculating the velocity at point B. So for that we need the crank speed. So we can see here the crank speed is 200 RPM, which is 20.9 radian per second. Then we can calculate VB by multiplying the speed of rotation by the length AB. So we can see here it's 314 millimeters per second. So now we are going to measure the velocity of C. So VC is equal to VB plus VCB. So by plotting the length of VB, then knowing the angle between VB and VCB, we can plot VCB, then we obtain VC. So here are the measures we obtained. And then we can calculate the crank speed at line 4, which is 11 radian per second. So for the acceleration analysis, we proceed as follows. So we know the expression of AC as point C does not rotate. We have a simplified expression of AC. So AC is equals to AB normal plus ACB normal plus ACT tangent. So now we can calculate AC with the crank speed of the line 2 and the length of AB, and ACBN with the crank speed of line 4 and the length of BC. Next, we measure AC and the tangential of ACB using the diagram here. We we can measure it like this, and then we can calculate alpha. So alpha is equal to 54 radians per second squared, clockwise.
Eventually, in this project, we explored the sewing machine's needle mechanisms, showcasing how rotary motion is transformed into precise linear and oscillatory motions for stitching. By combining theory with tools like CAD modeling, Excel for calculations, and ANSYS motion for simulations, we validated the mechanism's efficiency and performance. This study highlights the role of kinematic and dynamic analysis in understanding motion conversion and providing insights into the interaction of mechanical components. It was an excellent opportunity to enhance our skills in mechanical design, analytical thinking, and problem solving, preparing us for future challenges in engineering.
Thank you for your attention.